Hello everyone, I'm Farzin Piltan. I'm a postdoctoral professional researcher from University of Ulsan, South Korea. Now I'm going to present my research paper entitled An Adaptive Backstepping Digital Twin-Based Approach for Bearing Crack Size Identification using Acoustic Emission Signal. First of all, I explain about the objective in this research. The main problem in this research is developing a reliable technique for bearing crack size identification using an acoustic emission signal. To solve this problem, an adaptive backstepping digital twin is recommended. So why fault diagnosis is important? With the rapid development of technology and demand for faster industrialization, rotating machine has become more accurate, larger, and much more complicated. As a result, many faults can happen in the rotating machine, leading to expected breakdowns in the industrial systems. For example, an aircraft engine caught fire as it accelerated for takeoff, and Korean Air Flight 2708 at Japan's Honda Airport in May 2016. This happening could has been prevented if we have used robust, intelligent fault diagnosis system. Why motor fault diagnosis is important? Energy has an important role in our life. Around 50% of the energy that produced by various techniques are consumed by heavy industries, and one of the main devices of them are motors. Because of that, the condition monitoring and fault diagnosis is important factors for energy consumption. Why bearing fault diagnosis is important? Because we have two different types of the faults in the motor, mechanical and electrical. And bearing has around 69% of the mechanical faults in the bearing because of in the motors. Because of that, we focused on the bearing fault diagnosis in this research. We have 4 different faults in the bearing: inner, outer, roller, and cage. In this research, we focused on the inner, outer, and roller faults in the bearing. We have different techniques for collect the data in the bearing. For example, vibration sensors and CSA sensors, acoustic emission sensors, and temperature sensors. In this research, we use acoustic emission sensors to collect the data, and also we have different techniques for fault diagnosis in bearing, which can be divided into 4 main groups: model-based, signal processing technique, data-driven, and hybrid approach. In this research, we use hybrid approach for fault diagnosis in the bearing. The next question is, why digital twin? The digital twins are a relatively novel way to model physical systems. In these methods, physical systems are reliably modeled, and even the systems model can be used to generate the data. Digital twin technologies converting more popular. The digital twin are predicted to grow by about 38% and reach $16 billion by 2023. Digital twins are changing the style of work as achieved in various industries with diverse applications such as manufacturing, healthcare, and so on. The data set in this research, we use overlap data sets for testing the activity of the proposed method. In our data set, we have 8 different conditions and also 2 different crack sizes, 3 millimeters and 6 millimeters. Moreover, we have 2 different motor speed, 300 RPM and 500 RPM, and the data is collected by the acoustic emission sensors. These figures show the proposed algorithm. You can see here we have 3 main parts. The first part is adaptive backstepping digital twin. The second part is acoustic emission residual generator, and after that, classification. The adaptive backstepping digital twin divided into two main parts, modeling and estimator. After estimate the signal, the difference between estimated signal and also original signal calculated by acoustic emission residual generator. And finally, the support vector machine is used for classification. Acoustic emission signal in bearing is highly uncertain and nonlinear. Which technique is recommended for signal modeling? In this research, we use the combination of the Gaussian process regression and also fuzzy logic to modeling the signal and transfer the information from acoustic emission into the mathematical equation. The error of acoustic emission signal modeling using the proposed fuzzy Gaussian process regression and also Gaussian process regression is shows using this figure. You can see here the error in the fuzzy Gaussian process regression is less than the classical Gaussian process regression. Because of that, we use fuzzy Gaussian process regression for modeling the signal. After system modeling, the next challenge is developing a reliable observer to have a stable digital twin for crack size identification. So to do these things, first of all, we use the backstepping observer to improve the performance of system modeling. After that, to increase the accuracy and flexibility of backstepping observer, we use the neural network here. And the function of the neural network is defined by this equation. Finally, to improve the reliability and also robustness of the neural network backstepping observer, we use adaptive technique or online tuning technique by fuzzy logic algorithm. After estimating the signal using adaptive digital twin, we should generate the residual signal. The residual signal is generated by the difference between estimated signal and also original signal, and shows in this figure. After that, we can extract the energy features from the residual signal using this equation. And you can see here in this figure the all conditions of the signal. And you can see here in the proposed algorithm can detect all conditions of the energy which extracted from the residual signal. For classification the signal, we can use the support vector machine. And here you can see the two different algorithms, the comparison between the proposed algorithm and the neural backstepping algorithm. And you can see here the average accuracy when the motor speed is 300 is around 96 to 97%. And when the torque speed is 500 RPM, the average accuracy is 97 to 98%. Compared to other techniques, the proposed algorithm is more better than the other technique. In this work, the proposed adaptive backstepping digital twin and machine learning algorithm was proposed for bearing crack size identification. In the first step, the acoustic emission signal in normal condition was modeled using the fuzzy Gaussian process regression. Next, the adaptive backstepping technique was developed using the combination of the fuzzy Gaussian process regression and adaptive neural backstepping approach to estimate the acoustic emission signal in normal and abnormal condition. After that, the residual signal is generated by the difference between original and estimated signal. Finally, the fault decision part, the energy feature was extracted from the residual signal and support vector machine is suggested for fault classification. The result shows the accuracy of the fault diagnosis by the proposed adaptive backstepping digital twin approach is around 97%. In the future work, the robust backstepping approach will be developed to improve the performance of and robustness and adaptive digital twin.